My name is Chongzhou Fang. Today I'm going to present our recent work, Repttack. So cloud computing is nowadays very popular. Customers are able to utilize resources provided by public cloud providers in a pay-as-you-go manner so that they don't have to purchase any servers and build their infrastructures. However, this may lead to some security problems because there are resource sharing involved in this process, and this may lead to this may open the door for some possible attacks. For example, microarchitectural attacks like side channel attacks, transient execution attacks, or hammer attacks, and false attacks. They are or have been proved that it's feasible to deploy in a cloud environment. And they are all based on hardware design flaws, so it's very difficult to patch at hardware level. So in a paper published more than 10 years ago, this kind of the workflow of this kind of attack has been summarized as follows. So first of all, the attackers will first submit attack instances to the cloud, and then the cloud schedulers will schedule this attack instance to some node in the cluster, and then the attacker will try to determine if the victim instance is collocated by using technologies like network probing, etc. And then after that, once determining that the victim is collocated on the same physical node, they can start stealing information and interfere with victim program. So we can see that from this workflow that before attack, achieving collocation is required, is an important prerequisite. So it is important to study how to achieve collocation, but in previous literature, this step has always been assumed, and that they always used a brute force issuing to achieve collocation. But this is relatively easy to defend, and also high in cost. So the meaning of studying achieving collocation for attackers is that without specially designed collocation strategies, subsequent attacks are impossible, no matter how strong the attack is. Without collocation, you cannot make it run on. And also for defenders, it will be more efficient to defend at the scheduler level, because it's hard to patch at a physical level. But if we can prevent at the scheduler level, then it will be much easier. Because resource assigning and instance placement are done by cloud scheduler, it's important to study the vulnerabilities in the cloud scheduler. So the focus of this work will therefore be on the collocation step. And we don't consider how collocation is determined. Like we only issue this attack, and we do not care about the technologies that are used to determine collocation. And also, we don't consider how a specific type of attack works, because it's out of scope of this paper. So the threat model of our work, so for cloud providers, we assume a trusted cloud provider, so they don't work with the attackers, and they don't provide any assistance to the attackers. Instead they treat all users equally. And for users, we also assume that all users are equal, no matter malicious or not. And that is to say, the actions the attacker can take is limited to the same set of the normal users. However, we assume that attacker can have access to victim applications, which is a very possible scenario, because usually the program itself is not that sensitive, but the data and the service it provides is sensitive. And also, we assume that non-malicious users always try to optimize the scheduling outcome to get to run on the most suitable node, so that they can get highest performance. So the method here, we first introduced our targeted scheduler. So we assume that users, the scheduler works on some user submitted information like resource specifications, which refers to specifications like how many CPUs the users needs to use, how much memory is required, and affinity specifications that's like whether a application should or should not be placed on a node, and whether whether it should or should not be placed with some other applications. So this is the scheduler we target in this work. It's called filter score scheduler. It's a widely used type of scheduling pattern. It's used in Kubernetes and OpenStack, and there are two steps here: filtering and scoring, and they are both based on user specifications. So filtering steps first tries to find out a list of candidate nodes for the users and kicks out other nodes that does not meet the requirements, like they do not have enough resources or they do not match the affinity requirements users propose. And the scoring step basically just gives a score for every node in the candidate list and select the one with the highest score. So our attack strategy is shown in this slide. We exploit the scheduler features to increase the chance of getting collocation. So the first step of our attack is to infer victim submitted requirements and preferences. So if we recall our assumption, we see that attackers have access to user programs, so they can analyze their programs, and at the same time, users always try to optimize for performance. So it's possible for attackers to analyze their programs and try to find out what type of configurations the users may want to submit to the cloud provider. And then the next step will be to replicate these specifications and submit to the cloud scheduler while keep the resource requirements minimal, so that there won't be so that the collocation chances won't be missed because of resource conflicts. So this is why it's called Repttack, replication attacks. So here comes our evaluation. Our evaluation consists of two parts. The first part is simulation done in a Python simulator written by us. It's basically a behavior scheduler simulator, and it's based on it simulates the behavior of a filter score scheduler. And we read the source code of Kubernetes and tried to build a very similar strategy in our simulator. So in our simulation, server configurations are generated randomly, and applications are generated randomly, and there are a lot of unrelated applications running at the same time with victims and attackers in the system, so that we can simulate a cloud environment with multiple users and multiple attackers, multiple users and multiple applications running at the same time. And we also test our work on a cluster. Experiment is conducted on a Kubernetes cluster deployed on Cloud Lab. Server configuration, similar to our simulation, are done in a random manner, so that heterogeneous hardware features can be generated. And also applications are also randomly selected from popular Docker container apps, and user specifications are also generated randomly. So we first show our simulation result, and we show a single instance attack. So with this attack, we want to try to answer two questions. What are the factors that may affect attack success rate? And the second one is, how high can collocation rate reach? So we first vary the resource requirements users use in our system. We can see that when we vary the maximum resources the users in the system are allowed to use, the collocation rate basically remains at the same level, which means resource requirements does not relate to our success rate. However, when we change the affinity features in the system, users in the system that are allowed to use, the success rate varies a lot. So in this figure, the PMN and PMA refers to the probability of generating a affinity specification. So So we can see that as PMN and PMA increases, the collocation rate also increases accordingly. And we can see that the collocation rate can reach as high as around 70 to 80%, which is quite high for a single instance attack. So this means that when users are using these definitive features extensively, our success rate can be pretty high. Then we run multi-instance attack, which is more close to a real-world scenario. So we all want to answer this question: does increasing the number of attack instances improve attack success rate? The answer is absolutely yes. And by how? Well, how much? We try two different strategies. So the first one is we trivially just issue multiple instances, but with the replication step. And we can see that the collocation rate can increase by around 20% from like 45% to around 60%. But if we enforce a more carefully designed strategy, we try to introduce a new label called spreading label, which basically just tells the scheduler that attackers do not basically tells the scheduler that do not schedule my applications on the same node. In this way, the attackers can be able to spread their attack instances, and we can see that by using this strategy, the collocation rate can reach as high as as more than 90%. And with only 5 attack instances, the collocation rate can reach 80%. Then we basically repeat the same process in the real cluster, and we want to answer the same questions in a real-world scenario. So first we try to answer what factors that affect attack success rate. So affinity, as we know from the simulation result, affinity features that are used in the cloud environment does affect the collocation success rate. So we can see that the trend is similar to our previous result, and with affinity features used extensively, the collocation rate can be really high and can reach around 70%. And with multi-instance attack, the trend is also very similar. So we are able to reach around 80% in a with multi-instance attack with only 5 attack instances, as shown in the first figure. And we can see that the success rate does relate to the affinity features the users are using. And the success rate does not relate to other parameters like what is the application or what is the percentage of victims in the system or what is the total number of applications in the system. So now comes to the mitigation part. We want to patch the scheduler so that we can decrease the chance of attackers getting collocated with victims. So our proposed mitigation strategy is to introduce randomness. We randomly skip affinity checks during filtering step. So this strategy is quite intuitive. So because users are using heterogeneity during scheduling process, then the possible candidates can be narrowed down, and it's predictable by attackers. But now, if we randomly insert unrelated nodes to the schedule to the possible nodes, then we randomly insert and we manually enlarge the possible set of clusters of servers in the cluster. The collocation success rate should be decreased. The point here is we add randomness during this scheduling process. So how successful it is? We can see from the first two figures that by introducing this randomly skipping filtering step, we are able to decrease the collocation rate. And we can see that with only, if we keep the random skip parameter at 5% from the first figure, we can see that the collocation rate is dropped by around 60%. And the cost here is measured by the average number of violated specifications, and we can see from the table that even we tune the parameters to 20%, which means there are 20% of chance that a server may be introduced to the candidate list, even if it does not meet the requirements. The average number of violated specifications is only two. It's only 2, so which means there are 2 out of 10 labels that are violated. And if we can have control over those labels that we want to skip, like we add new restrictions to this mitigation strategy, the cost can be further lowered. So discussion. This work introduces a trade-off between security and performance. So letting users have control over scheduling outcomes can indeed bring better performance because users can choose to run on more suitable machines. But it brings worsened security because location in the cloud can now be relatively accurately determined. And also, we found a very interesting refined model or the diminishing return trend in the multi-instance attacks. So we can see that there is an optimal point for attackers. So before reaching this point, increasing the collocation rate is bounded by the number of attack instances. But if we increase the number of attack instances beyond this point, the gain in collocation rate won't be very high. And the position of this point is determined by user affinity usage situation. So we have some suggestions for cloud managers and users as well as attackers. So for cloud managers, we suggest that heterogeneity should be exposed as little as possible because it can be exploited by attackers, and they should bring randomness to scheduling process, even if that can bring some cost in performance or QoS. It does increase the security level by a lot. Also, for users, we suggest that users should utilize heterogeneity as little as possible unless they do have a very strict demand for performance. And also, they should keep their scheduling specification confidential because this kind of information can be utilized by attackers to achieve collocation and open the door for further microarchitectural attacks. For attackers, we suggest that they should study target applications carefully because they can help them better deduce what type of specifications they can propose. And also, when using multiple attack instances with different, using multiple attack instances, they can use different possible specifications to increase the coverage of the nodes in the cluster, so the collocation rate can be further increased. And also, they should be aware of the trade-off point in the number of attack instances, as we shown before. That can help them optimize for cost of attack. So finally, the conclusion. First of all, we propose that affinity features in filter score scheduler are prone to be exploited, and based on this, we propose Repttack, which is an attack method to increase the chance of achieving collocation in a heterogeneous cluster. And we propose a mitigation technology to defend against Repttack. And finally, based on all this information above, we provide the guidelines for cloud managers and users to increase the security of their service and applications. Thank you. That's all of my presentation.